Yeah, welcome to the NPA seminar today. It's my pleasure to introduce Manoa Andriamirado from the Illinois Institute of Technology. He is a graduate student on the Prospect experiment, the detector that we actually built here at Wright Lab and operated at HFIR for several years. And he's been working on the final oscillation analysis, and he will tell us about probing new physics with the Prospect reactor experiment.
Thank you for the introduction. So I'm gonna start. So as in all reactor neutrino talk, I have first to talk about neutrinos. So neutrinos are one of the most abundant particles in the universe, as they can be produced naturally during the Big Bang, in the Earth crust, in the sun. And they can also be produced artificially, such as at the accelerator and reactors. And depending on where the source that you use, you get different flavors. Accelerator, for example, may be producing flavored neutrinos, antineutrino in the GeV regime, whereas reactors only produce MEV electron antineutrino. Reactor antineutrino experiments have a good record track of scientific discovery and scientific achievements. And here I'm just highlighting a few of them. The first being the first detection of antineutrino was done at the Savannah experiment led by Cohen and Brains, which earned them the Nobel Prize. Then there is also the first observation of neutrino radiation from a reactor by Camlan. And then the measurement of theta 1-3 by Diabay, Camlan, CPK, SNO, and SuperK actually shared the Nobel Breakthrough Prize in 2016 for their work on neutrino oscillation. So how do we actually produce antineutrinos in the reactor? So we start by splitting the fission isotopes into fission products. And then this neutron-rich powder will undergo a beta decay while emitting antineutrinos. That means that 99% of the antineutrinos in nuclear reactors are from the beta decay of fission daughters of these four main isotopes here. And we usually categorize reactors based on the fuel that is burning. So for highly enriched reactor, or HEU, it only burns uranium-35. And for LEU or low enriched reactors, it is a mixture of these four isotopes here. And if we know what is burning in the reactor, in principle, we can determine what is the antineutrino spectrum from that reactor. And there are two ways to achieve that. The first one is called ab initio or summation method. And this is a ground-out method as we sum all the beta branches from all fission products using the database. But since we use database, there are some rare isotopes and beta branches that are still not measured yet. And that can lead to a large uncertainty in using with this method here. Here's an example when we use this method to predict the antineutrino spectrum from uranium-35. And each of these colorful curved spectrum here represent the beta branch. The second method is what we call the conversion method. So the idea for this is that we measure the beta spectra from the four isotopes that I mentioned in the last slide, and then we convert those into antineutrino spectra using periodic beta branches. The data that we use for the beta spectra data that we use for this method was measured in the 80s at the Yale reactor. So in 2011, there has been multiple efforts in order to improve the accuracy of the prediction of antineutrino spectrum. The first is in this paper here, where they combine summation and the conversion methods. The second one here introduces a few theoretical percentage level correction factor in the conversion method. And when we combine these two methods, it gave birth to the Huber mirror model that we use as the benchmark for all reactor experiments. Now, when they compare this new Huber mirror prediction with the previous measurements, then they saw about 5.7% flux deficit, and this is what we call reactor antineutrino anomaly. So it is illustrated in this plot here. This is more recent plot, but in general, we should be on this one here, meaning that the measurement and the prediction should match. But that's not what we see, as the global average, the global data average is around this orange line here. So what could be the origin of this flux deficit? Is it a miscalculation of the flux prediction? Because after all, it is a complicated calculation, and we're also missing some data in the database. Or it could also be that the antineutrino produced from the reactor oscillate into a fourth flavor neutrino that we call flavor neutrino, such that we cannot detect the enhanced flux deficit. And so the existence of this fourth flavor stereo neutrino is what we denote as the 3+1 model. So the 3 is for the standard neutrino, and 3+1 here is the sterile neutrino. And there are actually multiple hints that suggest that it could be the stereo neutrino assumption here. The first of those hints is the LSND minimum anomaly. So this one is the excess of electron neutrino from muon neutrino beam. So the LSND and the mini-Boone anomalies are two completely different experiments. They have different energy, different source on how the neutrinos are produced, and different predictors. But both of these experiments observe the same excess at low energy, which could suggest that it might be a stereo neutrino oscillation. Now, the second anomaly is what we call the Callium anomaly. And this one, rather than the excess, it's the deficit of electron neutrinos from radioactive sources deployed in Callium-based detector. The SAGE and the Galaxy and SAGE experiments are two solar neutrino experiments where they deployed intense radioactive sources in their detector to calibrate the detector. So chromium and argon. And what they saw is a deficit of the transition from the measured rate from the transition of Callium into germanium, which fits the scenario where there is a stereo neutrino oscillation. Now, these anomalies that I just talked about were measured in the past decades, and we have built many experiments in order to investigate the origin of these anomalies. So what is the current status of this anomaly for now? So if we look at the flux misprediction aspect of the reactor antineutrino anomaly, then it is fading away. So this is a very complicated plot, but the x-axis here is the measured rate for uranium-35 over the x-axis is the ratio of the measured rate for uranium-35 over the Huber-Miller model. And the y-axis is the same, but for plutonium-39. To interpret this plot, it is a bit complicated, but the gist of it is that if stereo neutrino is the origin of the array, then the data points should fall on this dashed line here, which is not the case. As the global data here indicates that there is another prediction of the uranium-35 rate in the Huber-Miller model, and that observation is actually supported by the fuel evolution measurement from Diabase. So that's in orange here. The new fusion beta measurement from the Kurchatov Institute, this brown here, and the summation method, which is the blue here. And in addition to that, the Huber-Miller model is also unable to precisely predict the shape of the antineutrino spectrum. As a comparison of the Huber-Miller model with the measured antineutrino spectrum shows the spectral distortion around 5 MeV here. And this is what we call as a bump in reactor neutrinos. Now, if we look at the stereo neutrino oscillation aspect of the array, then many of the suggested region from the array, which is in gray here, are mostly ruled out by many short-lived reactor antineutrino experiment, which you can see with this curve here. each of these exclusion curves represents the one experiment. So to interpret this plot, every oscillation parameters to the right of this curve are all excluded or rejected, ruled out. So as for the LSMP and the mini-boon anomaly, so the microboon is a large TPC experiment that running at Fermilab that is trying to find the origin of the mini-boon excess. And so far, I have not seen any excess yet that is due to neutrino interaction. But there are many photon and positron electron channels that remain to be unexplored, also including PSM physics. As for the LSMD anomaly, it has not been experimentally verified yet, but the GSNS2 in Japan is working on this, and we should hear from them soon. I'm not actually sure if they're taking data for that. So the gallium anomaly, so this one actually is being confirmed by the best experiment, and even we have higher significance now for sigma. So the best experiment has two targets, an inner targets and the outer targets, and both of them solve this deficit here in this plot. And there is also another experiment, reactor engineering experiment in Russia called Neutrino 4. And they reported the non-zero oscillation at high delta square here with a significance of 2.9 sigma. And the result is actually consistent with the gallium anomaly that I just mentioned here. Now, there are some notes on the validity and reliability of the Neutrino 4 analysis and results. So you can find in this link here, but I'm not going to talk about that later. So now I'm going to summarize all the measurements that we just saw. So most of the allowed suggested space for the gallium anomaly in blue here and the Neutrino 4 in red are mostly ruled out by short baseline measurements, as you can see with this exclusion. And if the gallium anomaly is due to the electron flavor disappearance, then how can the electron flavor reactor anomaly be fading away when we are using prediction other than the Hilbert mirror model or other prediction other based on based on the conversion method. So the blue here is the Hilbert mirror model. The allowed region here is from the Hilbert mirror model, and the green is HKSS is also based on the conversion method. And you can see that there is an overlap with the allowed anomaly here. But when we use, for example, a different method to predict the antineutrino spectrum, that is the EF, all of the suggested region for the gallium anomaly is ruled out. And now for the accelerator, as I mentioned in the few slides ago, the microboon experiment has not seen any excess yet. And for a 3+1 model, the suggested space by the LSMD experiment are ruled out also by a combination of muon and electron flavor disappearance from accelerator and reactor respectively. So that's the red exclusion curve. So the global view is really complicated as we see this strong tension between contradictory observations. So what can we actually do? It seems that the 3+1 model is not enough to explain all these anomalies. And around this SNOMAD 2022 the suggestion was to extend the 3+1 model to include more physics such as the coherence, decays, non-standard interaction, for example. In this plot here, when we consider the coherence effect on the neutrino oscillation, then it solves the electron disappearance tension, namely the array and the gallium anomaly. So in order to explore all of these models, we need a diverse program. And So that is in source and baseline energy and how the neutrinos are made. And the reactor is one of this program, this global program in order to contribute to solve the tension that we see. And part of the reactor program is Prospect, which I'm going to talk today. So the goal for Prospect, why we built it, is to share for certain associations as well as to perform a precise measurement of the antineutrino spectrum from uranium-235. And to do that, we deployed our detector at the High Flux facility at Oak Ridge National Laboratory. And the challenge that we faced for this experiment is that it is an on-surface deployment with minimal overburden. That means that we have a lot of backgrounds in our data that we need to remove. So the High Flux reactor, it operates at 85 megawatts. It is a HFIR reactor, meaning that 99% of the antineutrino is coming from that uranium-35. And the duty cycle is kept short, 24 days, after which we replace the fuel in order to avoid isotopic evolution. As you can see from this picture here, it is a very compact core, 20 centimeter in radius and 50 centimeter in height. And that is very ideal to go for high frequency oscillation when we also combine it with the short baseline deployment. So our detector covers the baseline from 7 to 9 meters. And we fill it with 4 tons of lithium-6 doped liquid scintillator. And then divided into a grid of 11 by 14 optically isolated segments. And that will allow us to perform a relative measurement for the neutrino oscillation. So each of the segments can perform its own, have its own spectrum, and then we compare that at the end. And we can also do visualization cut and cuts based on topology. And our detector can perform also 3D position reconstruction. So the X and Y is from the position of the segment, and the Z position reconstruction is enabled by the double-ended PMT result, since we attach 2 PMTs at both ends of each segment. We actually assembled the Prospect detector here at Yale, and we also deconstructed the Prospect detector here at Yale. So to detect antineutrinos, it is fully an inverse PLK process. So that is antineutrino coming in and then interact with free proton and then produce a positron and a neutron. So because of the mass difference of these two products here, the positron here carries most of the antineutrino energy, and it also interacts promptly near the interaction vertex. So we usually call this event the prompt signal. And as for the neutron here, it usually wanders around, and then 50 microseconds later, it is captured in the lithium. So because of that delay in time, we call this the delayed signal, the delayed signal. And to detect antineutrinos in our detector, we rely on these correlated coincidence signals. Now, this interaction will produce scintillation lights that are captured by the PMTs. And then when we look at the waveform in those PMT, we can actually tell what is the particle that induced the scintillation light. Here, for example, you can see that the nuclear recoil emits light longer than the electronic recoil. And the way to quantify this difference in pulse shape is through the PSD, or pulse shape discrimination. So that is charge of the tail divided charge of the full waveform. And this PSD information gives us a powerful, it is a powerful tool that we can use to identify NPA, as well as to reject backgrounds. So the plot here on the top is the PSD parameter, the function of the energy. You can see that there is an electronic recoil, nuclear recoil, and then we have this very localized peak here, and this corresponds to the neutron capture from the lithium event. So the Prospect data took from March 5th to October 6, 2018. So that is about 110 days of reactor on, 78 days of reactor off, 8 days of calibration. And we disregarded data from 36 visual segments experiencing current instabilities. I will come back to this later as what is this. But on average, we detected about 529 days of IBD per day. And when we look at the IBD rate in our detector, it follows on 1/R² distribution as it should be. So the top plot here is our collected events in blue as well as accidental background in red. You can see that we actually still detect correlated events even during when the reactor is up. So these are mostly backgrounds that we can use to determine what is the background for the reactor on. And with this data, we have published quite a few physics results, including our search for sterile neutrino as well as our measurement of neutrino spectrum. And this, the joint analysis for between diabatic prospect and sterile prospect to constrain the production from multiple isotopes were actually led by a previous student here at Yale. So what is actually new in this analysis here? What's new in the final prospect 1 oscillation analysis? So over the course of operation of prospect, a number of PMPs displayed current instabilities as the liquid scintillator ingressed into the PMP housing because of chemical incompatibility, and then interacted with the PMP circuitry. When we deconstructed the detector, we found out that some of the electronic components in the PMP divider were actually damaged because of this ingress, which you can see on these two pictures. So the plot here is the J channels that we had to turn off as a function of time. And at the end, about 20% of the total segment had to be turned off because they experienced this current instability here. And in the previous analysis, we did not use the data from any of the segments experiencing PMP current instability. And what we want to do in this final analysis is to use all the available data that is provided to us. And we do so by optimizing our data. So the first is to split the data. And the second is to apply a new event reconstruction called single-ended event reconstruction. So the goal for the data splitting is to recover data from segments before they experience current instabilities. And we do so by splitting our data into 5 distinct periods. So each of these periods now has its own detector configuration, detector response, as well as the list of excluded segments. In the previous analysis, we only had one detector configurations, which corresponds to the last detector configuration of last period here. Now, for some segments, only one of the PMTs experienced the current instabilities, while for others, both were affected. So the map here is the segment status of the last period. Green indicates that both of the PMTs were functional. Yellow, only one PMT were operative, and white, both of the segments were inoperative. So for only single-ended segments or only one PMT functional, we cannot reconstruct Z position as well as the energy because of that missing information from the other segments. But what single-ended segments can provide is PSD, because the PSD only relies on the full shape of your waveform. If we look at this PSD distribution here on the left is the double-ended segments. Both PMTs were functional, and on the right is single-ended segments or only one PMT functional. And you can see that we still see this separation here from the nuclear recoil and the electron recoil. So we can use that information in order to reject backgrounds. So here is the absolute spectrum. On the left is from the previous analysis, and on the right is the current analysis. So you can see that not only we increase our signal number of signal, but we also were able to decrease our background drastically, as you can compare with the two spectra. So what can we actually do with this data? In my case, the one that I'm going to present today, I'm going to present about the final oscillation search. So how do we perform that sterile oscillation search? So we, in Prospect, we combine spectra from several segments into baseline bin according to this map here. So the index and the color here represent the baseline index of that particular segment. So in this configuration, we use 6 baseline bins. And then we look at the spectral distortion at each baseline of the detector that is induced by sterile oscillation in the case where they exist. So here is just an example of what we might see in the case where it exists. So you can see that the spectrum per baseline also varies in shape as well as amplitude. But when we look at the real data, then it is very difficult to assess that. Here, it is only for one period, but we have 5 periods. So it's very difficult to visualize the full data set in the full analysis in the full analysis bin. But one way that we can summarize our full data set is to plot it in a simple and concise way, is to plot it in the baseline over average antineutrino energy. And you can see from this data that there is not really an obvious sign of oscillation. So it is consistent with the null oscillation. But to really quantify the preference of our data, we need to do a proper test statistics. And we use the combined element fusion as this minimize the bias introduced from a low statistics bin. And in addition to that, we also have to remove the reactor model dependency in our analysis. In other words, we perform a shape-only analysis. And we do so by relativizing our prediction according to this formula here. And you can see that there is a correlation between the first term here and the second term if you derive the statistical uncertainty from the Neyman. And there is also a correlation from the numerator and the denominator here if you derive your statistical uncertainty from the Pearson. And that needs to be taken into account in the statistical uncertainty. So once we perform that test statistics over the full grid point, then we found that our minimum chi-square is at this, or bispecific point is at this this grid point here at high chi-square. Now, when we compare our the chi-square of our bispecific point with the null oscillation hypothesis, it is only about 4 units of chi-square away from that. Does it mean that our data is compatible with null oscillation hypothesis? To answer that question, we need to do a frequentist test or Feldman-Cousin test, and that is to generate toys. So on the left here, this is the delta chi-square distribution of the null toy, and you can see that it is consistent with our data. And when we compare the delta chi-square of our data at neutrino for bispecific point with neutrino for toys, you can see that the delta chi-square from the toys are far below the observed data, indicating a highly inconsistency. And given the compatibility of our data with the null oscillation hypothesis, we can now draw an exclusion contour, which shows you which oscillation parameters are incompatible with our data set at 95% confidence level, shown by the solid blue here, and also at 5 sigma dash purple here. You can see that we reject the neutral for bispecific point at more than 5 sigma, and we also exclude all the phase space for the Galilean anomaly below delta m square of 10 EV at 95% confidence level. So by looking at the more global view of what the impact of our result is, so comparing our results to to short baseline reactor efforts, then you can see that we pretty much we set the word limit for in the range between 3 to 10 up to 20 EV squared. And for the and in this phase space here, the reactor-based limits are much more stronger than other experiment sectors, such as scattering, for example, in the green here, or microphone limit here. Okay, so what is next? The tension is still present, and we have not seen any sterile neutral oscillation yet. So, as I mentioned in a few slides ago, reactor experiments play a central piece in an integrated efforts to understand these anomalies, as reactor neutrino experiments are a pure source of NPA electron neutron disappearance. And so far, there is only three reactor neutrino experiments that plan to do an upgrade, and that is Tau under construction, Neutrino 4 Plus, and Prospect 2. And Prospect 2 will be the only US-based reactor Antineutrino experiment. So here I'm giving why we actually need to care for the short baseline electron feather disappearance here. Because of how neutrino mixes, the existence of this short baseline neutrino oscillation will also impact long baseline oscillation signatures such as the plots that you can see here are the expected event rate as a function of the neutrino energy. And you can see that there is an overlap between the 3+0 scenario that is in red here and the 3+1 scenario in the case where sterile neutrino exists. And this can actually cause an ambiguity as the origin of the observed event, whether it is only coming from the 3+0 or there is also a contribution from the 3+1 model. And in order to avoid that, we need to constrain the mixing angle θ1 4 and θ2 4 to less than 5 degrees. And Prospect 2 can measure this θ1 4 here very well. But before that, we first need to avoid the issue that we have with Prospect 1, and also improve the stability and the performance of our detector. And we do so by separating our PMPs from the active volume of the detector. And secondly, we are going to use this acrylic double-sealed acrylic window here to serve as the interface between the PMP and the liquid scintillator. And lastly, the optical grid of Prospect 2 will be of a similar design to Prospect 1, but without internal holes in order to maintain the detector uniformity. But because we have this, there is no internal hole here anymore, we now have to do our calibration externally. And we have published a paper where we actually detailed where we use Prospect 1 data in order to simulate this experiment calibration here, and the results were very promising. So we envision to deployment at the HU and the LU reactors. And here are the experimental parameters for those deployments. So we have Prospect 1, Prospect 2 at Hyper, Prospect 2 at an LU. The most important thing here is the statistics that you see in this red rectangle here, which increases as we deploy from the LU to from the HU to the LU. And using these statistics here, we can estimate what is the projected sensitivity for Prospect 2 in terms of oscillation. So in the deployment at Hyper only will address the main interest in oscillation phase space at high times squared here. So that includes the neutrino 4 allowed region here, and right. Prospect 2 will be also able to rule out most of the allowed region from the gallium anomaly below 15 EV squared. And we can also constrain the mixing angle θ1 4 between 1 to 10 EV squared for the long baseline CV violation interpretation. So the 5 degrees that I mentioned earlier, that is represented by this vertical line here. And compared to accelerator-based experiments such as the microboon, we have an unmatched performance below 20 ET squared. And because of the sheer statistics that we used to get from Prospect 2, we will be able, Prospect 2 sensitivity in black here will be able, will exceed Prospect 1, the final Prospect 1 sensitivity by a factor of 3 to 5. Now, when we combine the analysis from the HU and the LU deployment, this will enhance Prospect 2 oscillation physics goal even more, because we extend our sensitivity at low delta m squared here. That is thanks to the long baseline deployment from the LU, such that our sensitivity now is beyond the long baseline sensitivity ambiguity limit here in dashed gray line here. And with this, we can cover the parameter space between the diabase and the capturing, which is necessary for a global understanding of this CBD ambiguity limit here. So now I'm going to talk about a very different topic. This has nothing to do with sterile neutrino at all, but it is still within the BSM physics, and that is dark matter. So direct detection experiments focus on the GeV scale, and that's because these experiments lose sensitivity for light dark matters or sub-GeV dark matters, because the nuclear recoil kinetic energy is not enough to induce a detectable signal in the detector. And one way that we can overcome this issue is that if the light dark matters are obfuscated by energetic cosmic rays, such that the recoil has enough momentum in order to trigger a signal in both direct detection experiments as well as neutrino experiments. And this is the mechanism that we use for this sub-boosted dark matter search for Prospect. Excuse me. In Prospect, the boosted dark matter will scatters off of the free proton, and that will induce a high PSD single pulse event. So that is one event that is only contained within one cell in Prospect. But since our detector is subjected to a plethora of backgrounds, we need to remove those backgrounds. And we can apply a PSD cut since the gamma to remove, for example, gamma backgrounds, because the gamma has the gamma and the proton recoil have different PSD values. And cuts that we can also set is a single pulse requirement, since this will remove multiple neutron scattering from cosmic neutrons. And then the visualization to enable detector cell to shield them against neutrons that scatters at the outer edge of segments. So the data that we used for this analysis is about 2 weeks of reactor off dataset from March 18 to April 3rd. So this is just a subset, a very small subset of the entire Prospect dataset. And we excluded 28 of the 154 segments due to the current instabilities that I described a few slides ago. And once we apply the cuts and phytos that I talked in the last slide, we are able to reduce our background by 2.5 to 3.5 orders of magnitude, as you can see from this spectra here, where we apply our cuts sequentially. So at the end, we have this red spectrum here. At low energy here, we cannot really reject these backgrounds, as at low energy, most of the gamma events are now sneaking in the nuclear recoil band for the PSD, so that we can't really distinguish that. So for further analysis, it's preferable to just start from 1.5 MeV to 10 MeV. Now, as the Earth rotates, the boosted dark matter flux will reaching the detector is time independent, and we have determined that during the data taking, which is this state here, we have a high, we should expect a high signal period between 10 p.m. to 2 a.m. GMST, and the low signal period from 10 a.m. to 2 p.m. GMST. So before looking into the signal, and then we find out that there is a time variation, and we say hurrah. We first need to make sure that the cosmogenic background is not also time dependent. So one way that we can project that is to look at the neutron capture on the lithium, because this event happens quite frequently in our detector of a rate of 10 Hertz. So the plot here is the rate in time being, and the red is for the high flux period, and the black is the low flux period. And when we take the ratio of these two time periods, the expected level of modulation is 0.988, which is consistent to 1, meaning there is no time variation for this NLI event here. But we need to cross-check that with the non-signal data set. So we are looking at the events that is similar to the boosted dark matter in the outer segments here rather than the fiduciary segment here. And the high during the high signal period that is in red here, and the low signal period in black. And when we take the ratio of these two spectra and then feed the flat line to it, the bias is 0.988, which is consistent with the expectation from the NLA events here, and also consistent to 1. So we're now sure that there is no cosmogenic background variation at all. Now, if we look at our data, then there is not really no true sign of diurnal cellular modulation here. And similar to the National Oscillation analysis as well, we can set the exclusion limit based on the expected diurnal cellular modulation by comparing our data against time-dependent dark matter. So when we when we do the test statistics, here is the results that we have. And from this result, we can see that our result covers new space previously unprobed by other terrestrial experiments. The upper bound here is mainly due to the dark matter attenuation in the atmosphere, and the lower bound here is mainly limited by the dark matter interaction in the detector. So as a summary, with prospect experimental parameters and capability, we can search for new physics. In terms of stereo-neutrino oscillation analysis, we have now a world-leading limit in the stereo-neutrino oscillation analysis, as we have ruled out the recently claimed neutrino pore result at more than 5 sigma. And we also ruled out the gallium anomaly allowed region for L times square less than 1080 at 95% confidence level. And we mostly lead the limits for short wave electron flavor disappearance between 3 to 20 ED here. And to understand all the anomaly, the electron flavor disappearance anomaly, we need a diverse program. And Prospect 2 can contribute to this resolution here. And in terms of dark matter search, Prospect result covers regions of dark matter phase space unaddressed by previous terrestrial experiments. So that's all I have. Thank you.
Thanks, Manoa. Questions?
Yeah, nice talk, thanks. Around slide 30, when you compare your previous result, your new result, I think maybe 31 or 32. Yeah, that I agree. So the peak is that around 4.7 when you have the lithium 6 capture. Why?
This one.
Yeah, 4.7 one.
This one.
Yeah. So why? What's the difference there? Why is it disappear, or like why is it less prominent? Is just less data or something going on there?
That's a very good question. So, this is actually because we use the single-ended seg. So first of all, this peak here, it corresponds to the inelastic scattering of neutron on hadron 12. So from the inelastic scattering, the outgoing neutron can sneak into the neighboring segments. And if that neighboring segment is inactive in the previous analysis, we cannot reject that. But since now we are using this, the information from single-ended events, from single-ended segments, we can tell, oh, there's a coincidence between this neutron scattering here and this neutron scattering here and this neutron capture here. So we can reject that, and that's why we are seeing this very less prominent peak here from.
Okay, and I guess a follow-up question, because I thought this was a lithium capture or a neutron capture medium. I think I remember seeing it was a color map where you have the discrimination. I think it was PSD versus energy. Yeah, there, and so the lithium. So why does the lithium capture or the lithium neutron capture region disappears between the left and the right?
Yeah. So it comes from how we actually calculate the signal integral. It is square root of S0 and S1, where S0 is from the other PFTs and S1 is from the other PFT. So if you're missing that from the other, you're missing the information from the other PFT, then we cannot really reconstruct that peak there. So it is still present there, but we should not use it because it's not very localized, like in the double segment.
Got it. Thanks.
Questions? I had a question on page 48. You showed the Capturing limit, and I was wondering how much data taking or what timeline this corresponds to.
This is the expected capturing limits. So I believe this was in their paper on 2022, I believe. So yeah, I think that is the phase 1 and phase 2 projected sensitivity, I believe.
Then, do you have any more comments on neutrino 4? There's a little bit of parameter space that we weren't able to exclude from prospect. What can be done and what will be done in the future to go after this?
Well, I mean, the result is out there, and some people are very looking forward to it, and but we have demonstrated that it's not. We're lucky. We have not seen anything, and I think most multiple. No, actually, we are the only one that is looking to it. But sorry, what was the question again?
Well, what can be done to fully exclude neutrino 4? Any thoughts on that?
Well, I don't know. We excluded at more than 5 sigma. I think that's a very very good result. But with prospect 2, I think that so for prospect 1, you see that our sensitivity, we cannot really reject all the allowed region at 95% confidence level. So with prospect 2, we can actually do that and then say, oh, okay, we can even exclude this one here. So with more data, I believe that we can really rule out all the allowed region.
I wonder if you could talk a little more about the gallium anomaly that I guess spurs a lot of or motivates a lot of this. Like how much to believe it is a prediction error and like the cross section of that neutrino capture, given it's a large nucleus. And those are hard to quantify, even though it is a ground state to ground state transition for the most part.
I'm not sure I'm knowledgeable enough to really go dive into that. But I think I have seen some papers where they, instead of sterile neutrino only, I think they also introduce some decays, and it can only be possible at this gallium anomaly here. So I think that may be also some explanation, but the question that you answer, I don't think I'm knowledgeable enough to answer that.
Okay, another question. So in page 53, you talk about the where you talk about whether this might be a cosmogenic effect of the modulation. If I remember correctly, you expect about 1% modulation between summer and winter because of atmospheric temperature fluctuation. Is your data set that you're using here, what's the length of the data set?
It's 2 weeks, so we don't have to worry about that. Yeah. So yeah, even the GMST, even the GMT from GMST, it's not really. I think it was just about 4 minutes, I think. But yeah, it is just like 2 weeks, so we don't really have to worry about the variation.